In this lecture, we're going to use correlational analysis and regression analysis to bring some greater understanding to what is experienced around the world at the present time, and that's the COVID-19 pandemic. And so before we get into the correlation and regression analysis, we'll review some very basic things about COVID-19. And so COVID-19 is the disease. It's a respiratory disease caused by a virus. And so the virus has since been termed SARS-CoV-2. And this was a virus that was identified that started the pandemic around February 2020. So what is SARS-CoV-2? SARS stands for Severe Acute Respiratory Syndrome Coronavirus 2. And so this is a computer-generated image of the different components that makes up this particular virus that causes the COVID-19 disease. The two major aspects to this virus, which makes it so virulent and problematic, is contained within the genetic material, and that's the quote-unquote the RNA molecule that's inside the virus. And the virus is highly infective because of something that you may have heard about in the media or in other articles, and that's something called the S protein or the spike protein, which is the antigen that our immune system will attack if in an attempt to neutralize the effects of the virus. So in terms of understanding the dangers and the current state of the pandemic, statistics are generated, but it's important to find these statistics at valid, scientifically valid and reputable locations. One of the locations that is at the forefront of providing the most accurate representation of the statistics is the Johns Hopkins University Coronavirus Resource Center, which was developed and generated at the very start of the pandemic. And this is a website that provides a weekly update on the current state of the pandemic worldwide. So as of the week ending September 19th of 2021, the Johns Hopkins Resource Center reported over 230 million cases of infections worldwide and over 4.7 million deaths. In Canada, the case count as of September 19th, 2021 is over 1.6 million positive cases, which amounts to 4% of the total population of the country, with a death count of over 27,000 people, and that has to date a fatality rate of 1.7%. That is the percent number of deaths per number of positive cases. And so if we want to use correlation and regression analysis to get a handle and projecting what may potentially happen, we have to begin with an examination of historical data. And so this graph is a depiction of new SARS-CoV-2 infections in Canada over the weeks of July 18th through September 6, 2021. And if we look at the x-axis, these points represent weekly case counts in the entire country for the week ending July 18th all the way up to the week ending September 6, 2021. You'll see that the blue diamond symbols represent the actual number of reported cases for each successive week as reported by Johns Hopkins. The black line here is the black curve is the regression fit using a computer program, Microsoft Excel, that will, instead of generating a line of best fit, it generates a curve of best fit. And these data represent the latest quote-unquote fourth wave that has been taking place in Canada. Once again here, these data are sourced from the Johns Hopkins Coronavirus Resource Center, and so when examining data, it's critical to first understand where those data are coming from. And so what we see here in the sort of approaching the latter part of the summer, July 18th and the following weeks, we start to see a small increase or a rather slow increase in the number of weekly reported infections in Canada. And then we see on a week-to-week basis the number of reported weekly cases continues to rise. And what we're looking at here at the very end, this last data point, representing the number of cases for the week ending September 6, 2021, and it was reported that there were 25,342 new infections for the week that ends September 6, 2021. So to get an understanding of wondering or of examining if there's any pattern that appears to emerge, we use a computer-generated model that will try to capture the growth in these new infections. And the model that was used here is, as you can see, this is not the equation of a line, but it's the equation of a curve. And this is a third-order polynomial function, third order, named according to the predictor variable raised to the power of 3, and then another term where it's raised to the power of 2. We see a term raised to the power of 1 and a constant value, and these are all the coefficients that factor into this model. So the question that we can then use using this model is, can this model predict what is going to happen after September 6th? So this model was generated on September 6th, and you can see that it has a very, very strong correlation coefficient through the coefficient of determination of 0.9992, or can also be expressed as 99.92% of the fit to the raw data. Now, what we're seeing here is the same model that is used in a short term as a short term forecast model. So these are the same coefficients that were generated on September 6th, and the question that we're going to ask here is, can we use this model to predict what's going to happen after September 6th based upon the data that has accumulated up to September 6th. So what we see here in the blue the blue diamond symbols are not the actual data week to week, but these are the projected data that were estimated from the model. Remembering that the model the previous week had a fit of 0.9992, but of course the fit is going to be perfect when the data points are generated from the actual model. So the R-squared in this case doesn't actually help us out. So we have the projections depicted as symbols and as this curve. What the model predicted here is that an inflection point occurred on August 22nd of 2021. What the inflection point indicates here is that although after August 22nd, cases did continue to increase, but they did so in a decelerating fashion, as opposed to what happened here at the beginning, where the increase in cases was accelerating, in that there were proportionally more and more cases with each successive week. And even though the cases continued to increase after the inflection point, the week-to-week increase got smaller and smaller and smaller until it reaches a peak value. And so recall that the model was generated on September the 6th. So using the model, it was predicted that the number of weekly cases, or for the week ending September 12th, was predicted to be 28,773 new cases in Canada for that week. When it was reported by Johns Hopkins on that day, the actual number of cases was reported to be 27,716. So the model overpredicted what the actual case count was and was off by 5%. So that is one way in which regression modeling, nonlinear regression modeling, can be used in a forecasting sort of way. Now, continuing with our study of the current pandemic and how correlation analysis can help bring more information to light, we ask whether mitigation measures can help reduce the number of projected cases. And one such mitigation measure is the vaccination effort. And so when we think about the question, does COVID-19 vaccination work, we begin to think about how to ask the question from a research perspective. And so the answer to this question will certainly depend upon the type of research study. The first type of research study that can be conducted is something called an RCT, which stands for the Randomized Control Trial, for RCT. And this is the type of research design that does establish cause and effect. And this is the standard research design that is necessary for companies to obtain approval for the drugs before those drugs can actually get to market and available to consumers and patients. The RCT is considered the gold standard in research designs. It involves the use of an intervention. The intervention in a study like this would be the application of a vaccine. And that is something that is examined in the present. It doesn't use historical data, so the data are collected present and moving into the future. So how is a study like this carried out? Well, study volunteers would step forward, following a screening process, would be randomly assigned to a drug and or a placebo group. So one group of individuals would receive injections, as you see on the image here, on the picture, but the injection would contain everything the vaccine contains except for the medicinal ingredient that is key to the vaccine's function. The volunteers in both groups are then followed up for a number of months, and the outcome variable in a study like this would be the number of reported infections, illness, and, depending upon the study design, the severity of the illnesses. From these studies, efficacy is then determined mathematically. And so in answering that question, the vaccines are deemed to be either effective or ineffective, and are these results conclusive? Well, that would certainly depend on the outcome of the statistical analysis. The second approach that can be considered are using correlational studies. So it's important to understand with number one, that is not a correlational or regression type of study. But can we use correlational studies in this regard? Correlational studies, it is important to know that we would be using that approach to examine historical data. This is not cause and effect, but that does not necessarily dismiss this study design as one that could potentially add some meaningful interpretation to these types of research questions. And so this type of approach would examine previous outcomes, whereas the RCT is examining present day and future outcomes by following patients and following volunteers, rather, so following research participants moving forward. But with number two here, with the correlational approach, can the data collected from the past predict the future? And this is the approach that we're going to use in this next scatter plot. So what we're looking at here in this scatter plot is we have, once again, these data are sourced from Johns Hopkins. Along the x-axis, we have the vaccination rate in units of the percent of total population along the x-axis. And the question we're asking from a correlational perspective is, can this predict new infections expressed per 100,000 people in a country's as part of a country's population? It's important to express these data per 100,000 people because of the fact that different countries will have different populations. And so it's a way of standardizing it. So this scatter plot has taken data from the Johns Hopkins Coronavirus Resource Center and is examining the Pearson product moment correlation between these two variables for a number of countries. In fact, 158 countries reported their new infections and their vaccination rate, and these were data that were obtained on September 15th, and the new infections relate to the 28-day case count. So for the 28 days prior to September 15th, countries reported their new infections and then were expressed per 100,000 people. And so can R be calculated from this? So this outcome here, this equation is the line of best fit. This is the R squared value, and you can see here that there's quite a bit of scatter in the data about the line, and so the R squared value is 0.0459. Can we compute the PPMC from this R squared value? And yes, we can. But how do we do that? Well, we take the opposite approach to computing a square, and that's to take the square root of R squared. And so if you type 0.0459 into your calculator and hit the square root symbol, you'll get a PPMC, an R value of 0.214. Now, the strength here, this is considered to be weak to moderate, and I would refer you back to slide number 10 with our discussion on the various ranges to qualify certain PPMC values to their relationship strength. So the first thing we take a look at here in this equation is the direction. Anytime we have a correlational analysis from a scatter plot, we want to note the direction. The slope here is a positive number. And being a positive number, that's going to tell us that the slope, that the entire correlation is positive. And so the units here for the slope are the new infections, which is the Y variable, per vaccination rate. So with interpreting these data, so we have a positive correlation, a positive R of 0.214, and now we interpret this being a positive type of relationship. So this tells us that among 158 countries, that the countries that had a higher vaccination rate demonstrated a greater new infection count for the previous 28 days. And so that would seem counterintuitive to the idea or to the suggestion that vaccination has been a strong mitigation factor for new SARS-CoV-2 infections. But now, by examining the scatter, we might wonder that given that the R value is quite low, that if our conclusion is tenable or not. And what we're basically asking from that point, is the relation statistically significant? Well, to test correlation statistical significance, we go back to a previous technique that examined hypothesis testing. And so in our example here, we're asking the question, is there a statistically significant relationship between a country's vaccination rate and the 28-day new case count, so X and Y. So we're kind of going back to our basic symbols here. So we have 158 countries, and we calculated, or rather the computer calculated, the PPMC to be 0.214. So we always start with a statement of the null hypothesis. Now in this instance, we state the null hypothesis to be rho equals 0. Rho, R-H-O, is the lowercase Greek letter that is the symbol for the population correlation coefficient. Because it's going to be a null in the null hypothesis statement, we ignore the question and we always state the null the same way. That the null hypothesis states that there is no correlation between the two variables in question, and the alternative is that it is not going to be 0, that there will be a statistically significant correlation between the two variables in question. And so we see that the not equal sign is a suggestion that this is a non-directional hypothesis. So we're open to the possibility that the relationship here could be a significantly positive correlation or a significantly negative correlation. It could be direct or it could be inverse. Therefore, the advantage of using non-directional hypotheses for the alternative keeps the possibility that the difference could go in one or two directions. The next step is to calculate the degrees of freedom. And with correlation coefficients, the degree of freedom is always going to be n, which is the number of paired observations, subtract 2, because we have two variables. We have an x and a y. So we lose 1 degree of freedom with each variable. Because our total sample size was 158 countries, we subtract 2, and our degrees of freedom value is 156. We then go to the table of critical R values. So this is similar, has a similar idea to the Z table, except that this is an R table. And with the R table, what we're looking for is the degrees of freedom that we calculated, and it's always going to be an n minus 2. And we look for the level of statistical significance. And so alpha 2 means non-directional, whereas alpha 1 means directional. So we focus on alpha 2 because we decided to go with the non-directional approach and keeping our mind open to the possibility that it could be a positive correlation or it could be a negative correlation. And so we select the 0.05 level, and this has arbitrarily in history been the default level of statistical significance. So what we see here is that as the degrees of freedom number increases, which is reflective of an increase in sample size, so the number of pairs of data, we see that the critical R values, these are the R values that the study must generate, the calculated PPMC must achieve at least in order to have statistical significance. So we follow this down to the degrees of freedom in question. So this table only goes up to 100. Note that our degrees of freedom calculated was 156. That's off the table. But we take a look at that correlation coefficient regardless. We see that our correlation coefficient, for it to be statistically significant, must be at least 0.195 or greater. If it's less than that, then it's not deemed to be statistically significant. So as the sample size gets smaller and smaller, we see that in order for our relationship to be statistically significant, our calculated PPMC must be greater and greater. And so that's what we're going to focus here. So if we go back to our observed or our calculated R value of 0.214, our critical value for a degrees of freedom of 100. Ideally, we want to look for a degrees of freedom of 156, but that was off the table. So we'll stop at 100. We'll take a look at that, and that will tell us if there's a need to continue. And so with 95% confidence, our critical value of 0.195 is less than what we calculated. And because our observed value is greater than the critical value, at least at a degrees of freedom at 100, because we know that this value is going to continue decreasing, then we would conclude that there is a statistically significant relationship between a country's vaccination rate and the number of new COVID-19 reported infections in the 28-day period prior to September 15th. And so what we would conclude at this point is that there is a statistically significant positive relationship between a country's vaccination rate and the 28-day new SARS-CoV-2 infection rate. That indicates that a greater infection rate is related to higher vaccination rates, and we would follow this up with a statement that P is less than 0.05. So the probability that we would be committing a type 1 error is less than 5%. So this ends the last video of our Unit 4 lectures.